Now we are recording. Woo! Okay, here we go.
I got
Uniting
this.
case. This is where I think we're going to get to today. So here we go. We're going to prove that the power set of the naturals is equal to numerous to just the real numbers between 0 and 1. And the way we do this is, to remember how to do this. I basically know how. Yeah. So first of all, you have to take every real number, right? We normally think of the real numbers in decimal notation. You can write it as like points like 1, 5, 6, whatever, 2, 0, la 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 la, right? Okay, but let's not do that. Let's instead use binary. I want to say you didn't do this with Piper, right? Binary, like past the like, what's the fancy word for that point when you're not doing it in decimal anymore?
Mantissa.
Mantissa is the word for that? Okay. I don't know. Anyway, good. It's like this. So suppose I give you like 0.0, 1, 0, 1, 1, 1, 0, etc. Okay? So that's I keep wanting to call it binary decimal, but they scream at me when I say that because it's just wrong. So it's just binary. I feel like there needs to be a word there, but there isn't. Binary. Just writing it out in binary. Okay, this is, I claim, a real number between 0 and 1. If you've never seen this before and you don't get it, can someone explain, what is this, how am I supposed to interpret this? Woo, Peter!
It's like number 0.5s, and it just asks that number 0.5s at the add, then it's like 0.25.
Can't believe you're actually saying 0.5. Yeah, no halves.
Quarters.
One, yeah, so this is just a quarter plus no eighths, like a 16th, a 32nd, a 64th. And then like no, etc. Does everyone get that? That's like pretty self-explanatory for like man and kids. Woo, good. Well, now I think the bijection suggests itself immediately, right? Because give me a real number between 0 and 1 in binary. I'll just throw up a couple just so we can have fun. And maybe I'll do like 0.001101. Okay. Woo. What is this guy? Who gets it? Just use the infinite binary as a description of which friends to invite. Do I invite 0 to the party?
No.
No. Do I invite 1 to the party?
Yeah. Sure.
Yes. Do I invite 2 to the party?
Definitely not.
No. Do I invite 3 to the party?
You better.
Yes. And I invite 4, and I invite 5. Do I invite 6? No. Does everyone see that? You just interpret the 1 and the 0 as telling you whether to include or not include that number. And let's do another one. Here. Do I invite 0 to the party?
Yes.
Yes. Do I invite 1? No. Do I invite 2? Yes. Do I invite 3? Yes. No 4. No 5. But I do invite 6, etc. Okay, that seems like good enough, yeah? Okay, and this just is your bijection. To each subset of naturals, I have associated a unique real number between 0 and 1, and to each real number between 0 and 1, I have associated a subset of the naturals. All right, cool? That was pretty easy. All right. Woo. So, coming back up here, it is conventional, many people do this, like everyone, which is, since it's true that oh yeah, I guess you have to keep doing that, yeah. Since it's true that the power set of any set has cardinality equal to 2 to that set, then, and since we've just shown that the power set of the naturals is the same as the cardinality of the power set of the naturals is the same as the cardinality of the reals, then what people often say is that the cardinality of the reals is 2 to the aleph naught. Do you see how that's kind of like a convenient notation for that? 2 to the aleph naught is not literally, we're basically defining 2 to the aleph naught as being the cardinality of a set, which is the power set of a set of cardinality aleph naught. Who's with me? Woo! Okay. Quick detour. These next couple slides are not that important. So I might. No, see, that's what I don't want you to do.
Yeah, I can just
How
twist
did I end
it.
up with you doing this?
I mean, I can
Wait,
do
no,
it
no,
too,
don't
but-
twist it. Just don't. Just.
Okay.
It's okay if I walk off screen for a second. It's
Okay.
it's all right. I
keep it
still. Yeah, just leave it over here. Unless, Okay, good. Peter, I love you, man. Okay, good. All right, very, very fast. What's an algebraic number? You may or may not have heard of this before. Well, I'll tell you right now. An algebraic number is any number which is the root of a polynomial with integer coefficients. So wait, I actually do want you to rotate over here, because I would like to show you sort of how this works. This is sort of an important, has anyone ever heard of this term before? Algebraic versus transcendental? I feel like it comes up, but like, it's never actually explicitly taught. An algebraic number is any number which is the root of a polynomial with integer coefficients. So like root 2 is a algebraic number because root 2 is a solution of the function x squared minus 2. Yeah? Okay. So take this function. It has a root of root 2, so root 2 is algebraic. Take some crazy thing like the cube root of, such a rose example, 5 root 7 minus 1 minus 4 over 7 plus 9. Okay, loosely speaking, an algebraic number is any finite combinations of addition, multiplication, division, subtraction, and root taking. Okay, and to make this explicit, here's what I do. Gotta remember how to do this. Oh, so here's what you do. You just set this equal to x. And then you figure out what polynomial has this number as a solution. Well, can you figure out what to do? What should we do to x?
Subtract 9.
Yeah. So you take x and you subtract 9 and then multiply by 7 and then add 4 and then cube it. And then, when you add 1, and then divide by 5, sure. No, wait, before I divide by 5, I'm going to do one more thing. Because that gives you 5 root 7, yeah? Yeah? Now square both sides, just so I can avoid fractions. So if I square both sides, then I get 7x minus 9 plus 4, that whole crap cubed plus 1 squared equals 25 times 7, so that's like 175, and then just minus 175 equals 0. Boom! I just created, by like zoom, 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 an equation which is a polynomial and has a root, which is this number. Agree? Okay, and so if I just call this my polynomial, then that's a polynomial with has as a root. This is an algebraic number. Cool? Okay. Every number which is not algebraic is called, no, don't rotate.
Yes.
Is called transcendental. So a transcendental number, okay, and what numbers do you probably just want to guess are transcendental? Like pi and like crap like that. And you are right. Though it is very, very hard to prove that a number is in fact transcendental. This was like kind of an obsession of the 18th century, 19th century. And so the whole, how important is this? I don't know. What's the history of transcendental numbers? Leibniz is the first person to ever, remember that like it was a mere 300 years ago or something where Descartes is like finally is willing to consider numbers which are not just the result of Euclidean constructions. And Descartes is happy to graph things which are cubic equations and things like that, right? And the kind of stuff now that we teach you in pre-calc A and just assume that that it's so obvious, like, e to the x, for example, that's a transcendental function, as are all the trig functions. And there was no way to graph like the e to the x function or the sine or cosine function using a straight edge and compass. So it's Leibniz who first kind of gets obsessed with these transcendental functions. Okay, this guy Lambert proves that pi is irrational. It took all the way until then to prove that pi was irrational. He conjectures that pi and e are transcendental. And in 1844, this dude Louisville proves the existence of transcendental numbers. And the first transcendental number that is proved to be transcendental is this just crazy number, which is in fact just like, I'll show it to you. It's like point, so first of all, a rational number has a repeating decimal expansion, right? So any number which does not have a repeating decimal expansion is irrational. So Louisville constructs this number which is like, if I remember this correctly, it's like 0.1, and then it's like 0, 1, 0, 0, 1, 0, 0, 0, 1, something like this. So this is some artificial number, not a number that anyone ever cared about before. It has a pattern to it. Its decimal expansion has a pattern, but it's not repeated because the number of zeros, something like this, something in this, something like that. And he proves, that's the first transcendental number ever proved to be transcendental. The first number ever proved to be transcendental. But it's still not a number we like cared about initially. All the way until 1873, this guy proves that E is transcendental. Okay, Cantor shows, in fact, that the algebraic numbers are countable. This is important, so I thought when I made this presentation, because in 1874, he publishes his famous paper showing that the real numbers are uncountable. But he's so scared of saying something like the real numbers are uncountable, because even to be able to understand that sentence requires you believing that the real numbers are a completed totality. In other words, that there is such a thing as the set of real numbers in total, closed up, actual infinity. And he knows that people are going to freak out, and they freak out so hard when he talks about this. That instead, he writes his paper in 1874, and he titled it something like, An Algorithm to Produce Transcendental Numbers. And what he says is, what he actually proves in his paper, is that the algebraic numbers are countable, which I'm going to show you in a minute. Since the algebraic numbers are countable, in a freaking footnote, he proves that the real numbers are uncountable. And he just hopes no one will get too mad at him. And he claims, okay, well, since the algebraic numbers are countable and the real numbers are uncountable, then there must be an uncountable number of transcendental numbers. And in fact, in any interval, no matter how small, there exists a transcendental number in that interval. And in fact, his proof of the uncountability of the reals is actually sort of an algorithm for constructing one of these transcendental numbers. Okay, it takes another like 10 years or something for them to finally prove that pi is transcendental, and it is notoriously hard to prove that any particular number is transcendental. As of the writing of this presentation in 2017, we still could not prove that, for example, pi plus e is transcendental, although everyone suspects it is. Okay. In 1874, this is Cantor's first big paper. This is the first paper to take actual infinity seriously in the post-rigor era. He shows that the algebraic numbers are countable. He shows that the real numbers are uncountable, and therefore that, like I said, that every interval has infinitely many transcendental numbers, and that there are uncountable numbers. Okay, the proof of this. Okay, I don't really want to get into this right now, but you can actually sort of imagine how it works, right? What is an algebraic number? It's a root of a polynomial with integer coefficients. Okay. Well, what you can do is take all the polynomials of degree 0 with integer coefficients. How many are there? Those are all just the constant functions, right? So f of x equals 0, f of x equals 1, f of x equals negative 1, f of x equals 2, f of x equals negative 2. Does everyone agree that those are countable? Of course they are. Okay, now take all the polynomials of degree 1 with integer coefficients. So now that's just every polynomial like ax plus b, but where a and b are integers. Well, now you just go like 0, 1, 1, 0, 1, 1, 2, 1, negative 2, etc., etc., and you zigzag your way or whatever to listing out. Does everyone see? I'm going to just go really fast how you could list out every one of those. And then do with every polynomial of degree 3 and every polynomial of degree 4. And then every one of these polynomials has only n roots. And so then you zigzag through every single list of every single one of these polynomials. And thus there are a countable number of algebraic numbers. Who followed that? That was like, woo, good. If you want to see how this works kind of in general, or in particular, I guess, you can, this is sort of the enumeration. This is Cantor's enumeration, right? The simplest polynomial somehow is x. Then x plus 1, x minus 1, x plus 2, 2x plus 1, 2x minus 1, etc., etc. Eventually, you exhaust all the polynomials such that the sum of the coefficients has absolute value 3. Then you go to all the ones such that the sum of the coefficients has absolute value 4. And and you slowly work your way up to larger and larger polynomials with larger and larger coefficients. Who gets it, ish, or at least on some level? Okay, woo! His original proof that the real numbers are uncountable is not, interestingly, the one he is so famous for, the one involving diagonalization. He doesn't come up with that till like 20 years later. His first proof that the real numbers are uncountable is extremely confusing, and I learned it 1 year and forgot it, and I don't know it now. Woo. He continues publishing papers throughout the 19th century. From 1879 to 1884, he basically formalizes all of the modern concepts of set theory. He introduces cardinal numbers as a formal object of study. All the way, I think this to me is just shocking and insane. I mean, it's one thing for someone to this is just like look at this spread. This is like a 17-year spread. This is like some kind of LeBron career type thing, right? He himself is the first one to prove that there are an uncountable number of real numbers, and he just stays at the top of the field of set theory, the theory he created, for like 20 years. 17 years later, he comes up with diagonalization as the proof that we all now think of as like the proof that the reals are uncountable. And in fact, it's the thing that's going to come up again and again and again in this course, diagonalization. Meanwhile, he's in and out of mental hospitals like every couple of years, being attacked by his rivals for daring to treat actual infinity directly. He's blocked from all kinds of jobs that he wanted in various colleges throughout Germany. And he eventually just goes completely insane trying to prove the continuum hypothesis. Okay. What is the continuum hypothesis? Cantor what he wants to show is that the real numbers are the next possible biggest set of numbers. The continuum hypothesis says there exists no set whose size is greater than that of the naturals and less than that of the reals. And is this the end? Yeah. He can't prove this. And I'm going to just leave it open for a later week what happens to this continuum hypothesis. Very important. All right. David Hilbert, who kind of takes over as top mathematician from about 1895 to 1930 in the world. He is extremely pro-Cantor and writes, no one shall expel us from the paradise that Cantor has created. Other people beg to differ. Poincaré, big troll, we're going to have a whole presentation about him back in January, hates this and sort of hates rigor in general. And he takes a position that set theory is a disease from which later on we shall look back and be glad that we've recovered from. These are two famous quotes from the two different perspectives essentially on the formalization of mathematics into set theory. Okay, also Cantor is extremely religious, and it is impossible really to talk about, well, not impossible, but it's hard to understand his personal beliefs about set theory without understanding that he was sort of on some kind of quest from God. He believed that by ascending these higher levels of infinity, he was getting closer to God or something like that. And in fact felt that God had chosen him to sort of reveal infinity to the world. Anytime you come up with some new, you guys probably know this, anytime there's some actual science, there's just a whole bunch of stupid people out there who don't understand the science, but who turn it into some kind of thing astrology or whatever. So these infinitely sized sets of different sizes of infinity were seized upon by various religious authorities who felt that Cantor was somehow there could be only one infinite thing, which was God, and by claiming that there were actually different levels of infinity was tantamount to pantheism and it was heretical. Here we see some political cartoons from the time. This is God sort of giving Cantor the stigmata or whatever. This is an aleph and this is an omega, something which we're going to learn about next week.
Why are his hands like that?
What's up? It's like a, do you know what stigmata is? Like
Oh,
where your
oh,
like
never mind,
wrists
never
like
mind,
bleed
yeah,
from
yeah,
like
yeah.
the, I think that's what that's supposed to be. And then here is Cantor balancing on one of his olives between, on the one hand, I don't know who this is supposed to be actually, I forget, but this is Leopold Kronecker, his enemy, who taunts him and tries to destroy his career for daring to talk about infinity. And he's slowly kind of like going insane, and in fact it's quite a sad story in his life. He suffers from depression. He couldn't handle it when people criticized his work, which everyone was doing. At some point, he got obsessed with this late 19th century quest to prove that like Shakespeare didn't write any of Shakespeare's plays, and that they're actually written by like who's the guy? You know, there's like another guy that everyone claims that wrote all of Shakespeare's plays. I forget. If you said it, I would remember. Samuel something something. Don't you guys like learn? What's that class where all you do is read Shakespeare the whole year? Who's that one teacher that only does
Miss
Shakespeare?
O'Connor.
Yeah, O'Connor. Who's taking an O'Connor class?
She doesn't talk about the
they're
false
reading,
things,
though.
though. We only talk about
Crime and Punishment right now.
Woo! Okay, good. He died alone and sad in like a underfunded like World War I era German hospital, and really bad. Woo! Okay, but here's what's really good is the rest of this packet on countability. This is gonna blow your mind. What do we have left? 20 minutes. Perfect. Turn to, kind of a wild video a little bit. Turn to page, I guess, 3? No, 4? What does it say on the top? Prove that the union of an innumerable number of innumerable sets is innumerable. Innumerable is just another synonym for countable. Okay, so, why is this true? Someone give me the like fast version. Peter, what should we do? I haven't. What does it say on the paper? Before. We're going to finish this packet in the next 20 minutes. Prove that the union of an innumerable number of innumerable sets is innumerable. Okay. So we have a innumerable number of innumerable sets. So S1, Peter, you got this all on camera and stuff?
Yes, sir.
Okay, good. So these sets are all innumerable. We have an innumerable number of innumerable sets. Okay, what does it mean for these sets to be innumerable? Yeah, that there's a bijection between them and the naturals, or more casually, that they're listable. Oh, and I'll just write on the paper, S is the union among all integers I of all of these sets. So this is like the big union, right? This is the union. Don't fall asleep, no! I'm going to show that the union of all these sets is itself countable. Okay, well, let's just do it, man. Take the first, okay. So S1 is countable, right? What does it mean for S1 to be countable? It means we can list out all the elements. So let's call this like let's call this like S11 or some crap like that. Let S11 be the first element from set 1. And then let wait, did I already write this on the paper, how you're supposed to do this? No, I didn't. Okay, then let S21 be the second element from set S1. And then like S31 and S41 and S51, etc. Okay? Okay. What would be a bad bijection? What's like a dumb idea that doesn't work? Let's start with that. For how to list out every element. You guys even processing what's going on here? I have an innumerable number of innumerable sets. I union them all together. What's a way that doesn't work to list out every element in this S? Yeah, Simon.
Like take the first one from each and take the second one from each. Or sorry, no, take all of the first one, then take all of the second one.
Actually, neither of those things you said worked, right? What Simon said is, here's a bad explanation of how to list out every element in S. First, list every element in S1. See you later when you're done with that. Okay, you just never get to step 2. Follow? Okay, the other thing that Simon said was take the first element from every set. That also doesn't work because you're going to be doing that forever. Okay, so we have to do something more fancy. So I'm writing on my paper now. This kind of exactly Daphne gets it. So now take S12, S22, S32, S42, S52. What are these? these are all the elements from set S2. So right, this is set S1, this is set S2. By assumption, these sets are enumerable. And then we do it again, right? What is set S3? It's a bunch of it, so S1, 3. Is everyone grasping my notation, even though I'm not really explaining it well?
We're gonna zigzag.
Okay, and now, Daphne, what do? Zigzag, right? We just zigzag. We take the and eventually we'll hit every single element. Follow, say follow. Good, next. Making good time. Number, whatever, what number is it? 6. Okay. Prove that the set of finite strings from an enumerable alphabet is enumerable. Oh boy, this seems really important. Okay, so suppose we have a bunch of symbols. So we have like a symbol set. And, alright, if your set of symbols is finite, that's boring. Let's give ourselves an innumerable number of symbols. Okay? So, and here the notation gets a little bit tricky, so let's try to stay focused. So, let S1 be symbol 1. Okay? So these are like characters. I mean, that's just like comp sci or something. This is actually just, it's totally comp sci. But now instead we have it's like ASCII aleph not, right? Type situation. Cool, say cool. What are we gonna do? We're gonna make a string. Gotta finish this packet. What does this string look like? This string is, built into the definition of a string is, it is finite. Okay, so let's take an arbitrary string. So what we need to do is we need to show that the set of strings of the form x equals a1, a2, a3, up to an is enumerable. Okay. Would anyone like to casually talk about this? If I have an enumerable alphabet, why is the set of all finite strings enumerable? Well, the order in which the strings are occurring is okay. So I mean, it's kind of like the same thing as I was doing, I think, the other day, right? Given just the 26 letters of the English alphabet, how do you do it? List all possible strings of, I feel like this is the thing that's got to have come up before in comp sci, right? List every possible string using just the letters A through Z. What do you do? Okay, you can do like A, B, C, blah, 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 all the way up to Z, right? In other words, rank the strings by their length and also by alphabetical order. And when you get to the end, this is like what Excel does, like literally, right? Then go to AA, then AB, then AC, then... Okay, so does everyone feel that given the 26 letters of the English alphabet, there are a countable number of finite strings? Because you go through all the 2-digit ones, that's going to take 26 squared, then you go to all the cube. Okay, but that doesn't quite, so is everyone feeling it now a little bit? Okay, that doesn't quite work if the alphabet's enumerable though, right? Because then you can't, this never ends. So instead we have to do something a little more smooth. Simon.
Can you just do the same zigzag thing where every row is the length, the set of strings of the length I?
Exactly, right? You take all the strings of length 1, which are S1, S2, S3, S4, S5, forever. Then you take all the strings of length 2. So S1, 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 S2, S1, S3, etc. I think, no. I have to be a little more careful like that. That won't work. This way of listing them won't work, right? Because I'll never get past S1. So what do I have to do? I have to do the trick from last class with the skipping.
Yeah, that's what
Yeah. So this is S1, S1. Then I skip, and I go, here I go S1, S2. Then I go S1, S3. Who's following this conversation? Only by doing it this way, only by using the ordered pair trick from page 1 of this packet, will I be able to actually list out every string of length 2. Okay, and then I come back and I go here, this would be S2, S1, skip S2, S2. Okay, but if you agree that the set of ordered pairs of naturals is enumerable, then so should the set of all, these are essentially just ordered pairs of naturals. That's pretty much, yeah? And then you consider all the strings of length 3. So that would be like S1, 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 skip a space, S1, S1, S2, skip a space, etc., etc. These were all the strings of length 3. And then you just keep on doing that. Strings of length 4, strings of length 5, and then you zigzag. Okay. All right, long day, but I need you to keep paying attention for 5 minutes. I'm about to blow your mind. This is a method. There is a better method. The better method, so this is, I'm going to resolve this same problem, and this is like super deep and super important for what we're going to do in January. We're going to use the prime number coding method from the video from last class. So, take some string x equals a1, a2, a3, etc. Okay, now, the reason why this is really hard is that this represents the first character of this string x. This represents the second character of the string x. But I also have this set of symbols. Okay, so I have to now like convert. I have to like code them or something, right? So if a sub I is s sub j, oh boy. Okay. So in other words, let me just give an example. Suppose that example time. Example. Let my string be composed of, let the first character of my string be like the 7th symbol from my alphabet. Let the second character of my string be the 100th symbol from my alphabet. Like S3, S9, S1, S15, and I'll stop at like S like 17. Okay, does everyone agree that is a finite string? Okay, now what we're going to do is we are going to convert this finite string into a number. We're going to code it. And we're going to code it using the primes. So create a gigantic number which is 2 to the index of the first character, the index of the first character. Take the index of take the index of the first character from the string, but the index of that character in the list of the symbols. Why do I'm having trouble saying this? So in other words, 2 to the 7th times 3 to the, take the power of 3 to be the index of the second character from your